Welcome to my talk about the paper Offloading Safety and Mission-Critical Tasks via Unreliable Connections. My name is Schönberger and this is a joint work with Georg von der Brüggen, Kuan-Hsun Chen, Benjamin Sliwa, Hazem Youssef, Aswin Ramachandran, Christian Wietfeld, Chen Hompel and Chen. Today we first look at a short motivational example, then have a look at the system model before I explain the actual technical contribution, which are two recovery protocols. We discuss their timing analysis before I show you some results of our experimental evaluation. So, what is this all about? Consider a robot that executes multiple tasks such as moving, laser scanning, and trajectory planning. And we assume that for the trajectory planning it needs some kind of cloud assistance and therefore offloads some part of its workload using a wireless connection. Accordingly, the robot is completely dependent on the connectivity, and without connectivity, this could easily end up in a collision. So the question we answered in our paper and would like to answer now is how to safely offload critical tasks. For the rest of this talk, we consider the following system model. We consider a set of tasks comprising a set of critical and a set of non-critical tasks. So the critical ones are safety and mission-critical tasks and need to have their timing requirements satisfied at any point in time. Moreover, we assume that the offloading decision is known and was made at design time. We model each task as a self-suspending task with one so-called suspension interval and with two computation segments. And each task tau k has a release time rk, a finishing time fk, a relative deadline dk, and a minimum inter-arrival time tk. So since some reviewers complain that our notation is a little bit complicated, we try to simplify it a bit and to make it a little bit more intuitive. Accordingly, in a task, the first computation segment is executed locally, and afterwards we have the so-called pre-processing phase, which takes place before a task is offloaded. Then we have the suspension time, which is the time in which the task is actually offloaded and executed remotely. Then the post-processing phase follows after a response has been received from the remote server, and finally the second computation segment that is executed on the local system. So now we know how to model task offloading. Now let's have a look at what happens if a connection is unreliable. If we offload a task, we expect a response from the server until a pre-specified point in time. This is not received, we know that something went wrong, which is very likely to be a connection issue. So in this point of time, which we call T down, the system needs to adapt its behavior in a so-called behavior switch, which needs to follow a pre-specified protocol. We offer two protocols for this case. The first one is the service protocol, which aims to provide as much service for non-critical tasks even after a behavior switch. The second one is the so-called return protocol, which aims to return to the normal system behavior. That means the offloading behavior as fast as possible. Under the service protocol, the system reacts to the situation by performing a local re-execution of the task share that was originally offloaded, and afterwards we execute the second computation segment as usual. For the next task instance, as well as for all other task instances of any task released after or at T down, also no offloading is performed. This behavior is the same independent if a task is critical or non-critical. Offloading is activated again when either the system idles or the system idles with respect to the critical tasks. Both of these are options that can be configured. So when the task is not offloaded, this is called the local execution behavior, in contrast to the normal offloading case, which we note as normal execution behavior. Under the return protocol, we actually have the same if a task is a critical task. For non-critical tasks, it differs from the service protocol in such a way that no re-execution is ever performed for any non-critical task. And even under local execution behavior, non-critical tasks are still offloaded. This is because offloading here helps us to detect if the wireless connection is re-established and also helps to return faster to the normal execution behavior. Now we know how the protocols work, but we still need to verify the timing behavior of the system. So if you expect detailed explanations, I'm afraid I have to disappoint you, since I don't want to bore anyone off with formulas and equations and stuff like that. And instead I will just give an overview about our analysis strategy. And if you're interested in the details, please read our paper. So, first of all, we need to ask ourselves, what do we already know? We know, for example, that an offloading task that is executed under normal behavior is a self-suspending task. And for such tasks, there already exist methods for analysis in the literature that can be reused. We also know that a task under local execution behavior is basically a normal sporadic task for which also analysis methods exist that can be reused. And we also know that for non-critical tasks, we don't have any timing guarantees that we give under local behavior, so we don't need to focus on this in our analysis. Let's focus on the analysis of the service protocol now. For a critical task, tau k, we'll look at the time interval from its release time to its finishing time, and we know from the specification of the service protocol that in this time interval at most one behavior switch can occur. Based on this, we can enumerate all possible system states during the time interval from rk to fk in which at most one behavior switch occurs. So first, the system could exhibit local behavior at time rk and normal behavior at time fk, which we denote L to n for local to normal. Second, the system could exhibit normal behavior at time rk and normal behavior at time fk, which is n to n. Third, the system could exhibit normal behavior at time rk and local behavior at time fk, which is n to l. And last, the system could exhibit local behavior at time rk and local behavior at time fk, which is L to L. If we take a closer look at these cases, the first thing that we realize is that case L to N is not possible according to the specifications of the protocol. So to switch from local to normal behavior, it is necessary that the system either idles or idles with respect to the critical tasks, which cannot be possible since task tau k is active and is not yet finished. So, also case n to n turns out to be a standard case of systems with self-suspending tasks, so that we can basically apply existing analyses here and do not need to consider this further. Therefore, we only need to investigate the cases n to l and l to l. If we analyze case n to l, we can find out that the worst case response time of tau k in this case, that is fk minus rk, is upper bounded by the summation of the first computation segment, the pre-processing phase, the local re-execution of the originally offloaded task share, the second computation segment, and the higher priority interference. If we then analyze case L to L, we see that the worst case response time is upper bounded by the summation of the first computation segment, the local execution of the offloaded task share, the second computation segment, and the higher priority interference, which is dominated by case N to L. Yeah, believe me or read the proof. So that means we only need to consider the timing of the system in case N to L and need only to verify this case. Things are quite similar under the return protocol, except that the high priority interference must be considered for critical and non-critical tasks individually, since due to the lack of re-executions that are performed for non-critical tasks, the analysis would be pessimistic otherwise. To evaluate our protocols, we performed different experiments. First, we used synthetic task sets, where we had 10 tasks per task set, utilization values generated according to U-unifast, periods over a log uniform distribution. We also created suspension intervals according to a uniform distribution, divided the execution time values we got from the above values into computation segment, generated an execution time for the locally executed segment that would usually be offloaded using a scaling factor and a suspension time. We assigned rate monotonic task level priorities. We modeled the offloading, so the probability that an offloading operation is unsuccessful, so the unreliability of the connection, using a Poisson distribution, and we tested different values for this one, and we simulated this whole system in an event-based misrate simulator. And each experiment, that means the experiment for each setup basically, was repeated 100 times. Moreover, we considered a Robotnik RB1 base robot platform, which is a robot from logistics used for loading, and this robot also needs to navigate in highly unstructured environments. It's running ROS, and we basically used a simulation of the navigation in a virtual map using a gazebo-based environment. We measured the timing data, and then based on this, we retrieved 3 periodic implicit deadline tasks regarding the navigation of the robot. These were transformed into self-suspending tasks according to the first experiment, and we simulated this one also in an event-based misrate simulator with one setting for the connectivity problem probability. So this experiment was also repeated 100 times. The first thing I want to show are the acceptance ratios for both protocols as a function of the system utilization for task sets with 20% critical tasks, which are quite reasonable. What we can see here is that the acceptance ratios of the service protocol are clearly lower than of the return protocol, which is a result of the different handling of non-critical tasks under both protocols. Here we can see the percentage of time the system exhibits local execution behavior under different configurations of the probability of unsuccessful offloading operations. On the left we see the result for the service protocol, on the right for the return protocol, both for the same scenario of 30% system utilization and 20% critical tasks. There are 2 things we can notice here. First, under the service protocol, the system spends much more time on the local execution behavior compared to the return protocol, which is actually what was expected, since the service protocol serves non-critical tasks while the return protocol basically aborts them under local execution behavior. So second, the higher the probability of an unsuccessful offloading operation, the more time the system exhibits local execution behavior. Finally, we see the percentage of time the system exhibits local execution behavior for our robot experiment. Here we again consider different probabilities of unsuccessful offloading operations, and for a scenario in which 20% of a task is offloaded, we observe the same as in the previous figures. So the higher the probability of an unsuccessful offloading operation is, the more time is spent exhibiting local execution behavior, where the percentage of time is in general lower for the return protocol. If we compare this to the case in which 60% of a task is offloaded, we can clearly see that an increase under both protocols is achieved, which means that the time the system exhibits local execution behavior is also strongly dependent on how much workload is actually offloaded. What should you take home from this talk? Well, there are cases in which offloading is necessary and even crucial. And in such cases, you can offload even critical tasks, and this can be safe if you use a suitable protocol and if you verify the timing behavior. For example, you can use our proposed protocols and analysis. The other thing is, control your suspension. That means basically take into consideration that the properties of a task system and your decision which task is offloaded when, for how much time, will strongly impact the behavior of your system if it suffers from connection issues. So make these decisions very carefully. Thank you very much.